Okay, so this short video module will discuss chi-squared tests. Start as soon. Before we begin, I'd like to mention that I have no knowledge of your exam, your course, professor. This video is for general knowledge purposes only, and it's not affiliated with any course or program. Also, most of the images used in this video are not my own, unless stated otherwise. And if you find any mistakes in this video, please let me know, and I will try to correct them as soon as possible. We can start with an overview of chi-square tests. So chi-square tests are also called chi-square tests, so squared or square is the same thing. The particular test we're going to be looking at is Pearson's chi-square tests, also known as chi-squared goodness of fit tests or chi-squared test for independence. It's all the same thing. And it's used with independent categorical data. So these are things like blood type, university affiliation, and religion. So these are I guess, variables without any gradient scale or numerical orientation. It's very well defined. Blood type, you're either A, B, or O. There's no switching between the two. There's no one is better than the other or more expensive or higher or anything like that. They're very separate, distinct categories when we're doing a chi-square test. Chi-square test is used to determine the probability that differences between categories of those categorical variables arose by chance. So when you do your study, what's the probability that there's really no difference and that all the variation you see is due by chance? So, for an example we can consider is a hypothetical study looking at religious affiliation by university. So let's say that researchers have found that there's a large number of Catholics at University A, while there's a large number of Muslims at University B. And after collecting this information, the researchers want to know whether they have enough evidence to conclude that a difference in religious affiliation between the two student bodies is large enough to be attributed to chance. So because they're looking at categorical data, which is probably independent of each other, we can use a chi-square test to tell us the probability of this difference being due to chance. Questions. So the first thing we can look at is exactly how a chi-square test is performed. Now you can do this either by hand or with a calculator, or you can do it with a computer program. And I think it's good to know both, just so you can really understand how the test works and the implications of performing this test. So the first thing we can look at is using a computer program such as SPSS, as I believe many of you have used in this course. And after you've inputted your data, you can go to the statistics menu, I guess, and select the chi-square option. After that, you'll have this option pop up, and you want to ensure that you've checked the observed box for counts, just to make sure that your chi-square test turns out the right way. After you do this, you might get a reading similar to this one. And what we're really interested in here is this top line that says Pearson chi-square, and we'll look at how to read this in a little bit. But this is really the only part of this particular diagram we're going to be interested in at this time. Now, in addition to SPSS, you can also do chi-square tests on very basic Excel using the command chi-test in older versions or chi-sq period test in newer versions, though both commands seem to work well on most computers. So that's just another option if you're interested in performing that sort of test, I guess, on a computer which doesn't have SPSS. So this is the formula if you were interested in performing the calculations by hand. So you'll notice we have O's and E's. O stand for observed values, E stand for expected values. And what we're going to do here is take the observed value, or the value that you find in your study, and subtract from it the expected value, or what you would expect the value to be if there was no differences. All the differences you saw were completely by chance, and we'll see how to calculate this E in a second. So after you take your first value or data point, O minus E, square that, divide again by the expected value. You do this for all of your data points, and then you add them up. That's what the sigma means. You add them up, you take the sum of it. and that sum is going to be a chi-squared statistic, and we'll see how to interpret that in a little bit. So going back to our example of University A and University B and religious affiliation, we can take this very hypothetical data set. Now just looking at this data set, you can see gross differences between University A student population and University B. But just to walk you through the example, the first thing we want to do when doing a chi-squared test is calculate the total column counts. So looking at basically the sum of each column and the sum of each row, and then the total sum that we have. And just to emphasize the fact that when I say there's no difference due to chance, when we see the expected cell count, I'm referring to the null being completely correct. I'm not referring to t-tests or anything like that. I hope that makes sense. After we have this, we can then do our calculation and get our chi-squared test statistic. Now, some assumptions that you might want to consider before going into a chi-squared test. You need to assume a simple random sample population. So you have no biases in your selection of your population or anything like that. You also want to assume that your sample size is large enough to answer your question, so you do have enough power. And neither of those can be answered by the chi-square test, so it's just something that you'll have to consider before you actually start the test. Chi-square test is for independent data, which means no matched pairs, no correlated data. You can't use twins with a chi-square test, so if you have twins or matched pairs, you might consider something like a McNemar's test, which is different. So you want to be sure that you're separating the two of them. And finally, when you have a chi-square test, you need adequate expected cell counts of at least 5. And if you don't have at least 5 in each expected cell, don't worry, you can use in here. So Yates continuity correction is used when the expected cell counts are less than 5. In this correction, you're going to subtract 0.5 from the absolute value of your observed minus your expected before you square. So absolute value just means you remove the plus or negative sign, which might be present in front of this difference before you subtract your 0.5. So everything becomes positive within this absolute value sign. Other than that, the dividing by expected and the summing of everything up is exactly the same. Now, Yates continuity correction is often criticized as being too conservative, which means that there's a greater probability of a type 2 error. In terms of this chi-squared test, this means we're more likely to conclude that the difference between the two groups is due to chance, when in fact it is not, and there is appreciable difference between the two groups. So just be aware that Yates continuity correction is sometimes seen as overly conservative. Go back to here. If your chi-squared test comes out positive, it means that you're going to reject the null. What was the null? That the difference is due to chance. So if you get a positive or a significant p-value here, you can safely conclude that your difference is not due to chance, so there is probably a difference between the two groups. Hope that makes sense. If it doesn't, let me know. If you see a mistake, let me know, and I'll try and fix it. Okay, thank you, and I guess that concludes this video.